record on this computer. There we go. Very good. Thanks for asking. Now, I lost my window here. There we go. Let's see. Participants, there I can see who you are. And where's my chat? All right, now I can see what's going on. Got record going? All right. So back to the start again, brief review of factorial designs for those of you who weren't here when I didn't start recording, and now that I have started recording. Factorial designs we want to think of in terms of treatment components, because the type of industry we are in, it is very frequent to have our treatments not be a single thing. They are combinations of things. And if they're combinations of like things, then we can classify the like things into factors. Adjuvants are a class of factor as opposed to an active ingredient. That's a different type of factor. And then within that, we would have multiple levels. That gives us an opportunity to look at the main component effects or main treatment effects and then look for interactions among components. And we need to have all possible combinations of levels of factors represented in order to make it a factorial design. There are very common cases where we have treatment structure. I see experiments with treatment structures that have multiple components, but they are not balanced across the different treatments. So it's hard for us to piece out what each component does individually. And the randomization in standard factorial experiments are that the factors are randomized independently in combinations, which makes it equivalent to RCB if each combination of factors is considered a treatment. And the converse of this probably won't make, well, I might touch on a little bit today, is that if we see that there are combinations of treatments among a multi-treatment study, if there are some combinations that appear more than once, we can think about converting an RCB or standard randomized complete block design experiment with a or into a factorial design simply by restructuring the treatments. The analysis of variance, our replicates or our blocks, works out the same way in a standard factorial design, but our treatments are decomposed into main effects and into interaction. And so an example I give of this, I have a 6-treatment trial in 6 replicates. Uh-oh, something's wrong here. I have the wrong table here. Let's ignore this one because I'm going to show you what the actual ANOVA table looks like instead. Yeah, there we go. You know what? Here's the great thing about computer technology. We're just going to go ahead and fix it. There we go. So the standard randomized complete block design ANOVA table, what we want to look at here is that our treatments, we have 5 degrees of treatments. Oh. I've got 2 new people joining, letting them come in. We have 6 treatments and 6 replicates. That means our block degrees of freedom is 6 minus 1, and our treatment degree of freedom is 6 minus 1. And our error works out to be 6 minus 1 times 6 minus 1. All right, it's the combination of it's the interaction between treatments and blocks. Although since we don't have any other observations, we don't have any other degrees of freedom for error, so we never decompose that or explicitly state that as block by treatment interaction. Okay. Now, when we move on to the same type of treatment structure, but grouped into components, so 3 treatments by 2 treatments, we get the same replicate and error sums of squares, but our treatments are decomposed into the components, which there's 3 components, so there's 2 degrees of freedom, and 1 component for B is 1 degree, 3 components for factor A, so there's 2 degrees of freedom there, 2 components for factor B, so there's 1 degree of freedom, and since we had 5 degrees of freedom total, we end up with 2 degrees of freedom for the interaction part. Okay. And I'm skimming this real briefly because we'll get into some example trials and maybe make that a little more clear. And so again, just to highlight this difference, our between blocks or replicate sums of squares works out to be the same for both. Our error sum of the square works out to be the same, whether we analyze it as RCB or factorial. But our treatment sums of squares are decomposed into different components. Okay. So this should be a fairly brief review of that. And before we move on to the split plot part, let's go ahead and look at an experiment that I've used before that illustrates the benefits of factorial designs. So I have on my machine, and I hope you now see, it should say 6 shoe trial RCB. And Matt, I'll trust you to bump me a message if you're not seeing what we need to see here. Matt should be familiar with this. This is an experiment I did on myself. And the brief story of this is I started a project years ago where I decided I was going to run every day. And so I did. I ran every day. And after about 10 months of that, I got bored because running every day the same roads over and again out in the country gets a little tedious. So I decided I was going to do an experiment. And this is a time when I was starting to develop some of these methods for different experimental designs and looking for different type of experiments so that I could get a handle on how to do randomizations and blocking. And so I came up with a plan that I was going to run 6 days a week, that I was going to record as my experimental running days. And then on the 7th day, Sunday, was going to be just a light, easy run that didn't count. So that gave me a 6 treatment structure because each running week would be a complete block. And then I decided to do it as a Latin square just to make sure that my running treatments were balanced by days of the week. So Monday was one thing, Tuesday was another thing, Wednesday was a third thing. And I wanted to make sure that all of my treatments were balanced. We don't need to worry about the Latin square part of this because we're going to analyze this as RCB. But we do want to recognize that there are 6 treatments in this design, and they are named by their shoe type: Lunar Swift, Ghost, Green Silence, Lunar Fly, Launch, and Lunar Racer. Now, I kind of picked among different types of running shoes. So there are cushion trainers in here, and there are racing flats, and there are lightweight trainers, and there are different brands. Okay. So if we do the analysis as an RCB, and we'll just go to the means table. I've got Tukey's HSD, and actually for our purposes, Tukey's HSD and LSD won't be much different because there are only 3, or well, there are very few combinations. Well, I'm sorry, and this one Tukey's might make a difference because we do have 6 treatments. But this is a fairly straightforward analysis, and I'm going to go ahead and print the report. And what we're going to really be looking at today are 2 things. One is our ANOVA table, and we're going to be looking for running speed, which is my measure of what's most important about running shoe. I don't care if a running shoe looks good, if it's slow. So I want to know if there is a significant difference among my treatments, and there is indeed a significant difference among my treatments. There is also a significant difference in my replicates. That was because this occurred over a period of several weeks, and it went from fall weather to winter weather. And sometimes in South Dakota, it gets cold really quickly. Now, I'm making that as an aside because I think we're looking at a stretch of weather in the teens over the next few days. So this is almost December weather. Oh. All right, I got a message about background noise, so I went ahead and muted. So sorry about catching that. I hope we're clear now. All right, so we have significant treatment effects for running speed. If we go look at our mean separation letters, we can see that there are indeed letters, but to be honest, they're not particularly informative. I have one shoe, Lunar Racer, that is different than another shoe, Ghost. That's the only real single pair difference I can talk about. Now, the problem with this comparison as it is Ghost is a cushion trainer and it's produced by Brooks running shoes, where Lunar Racer is a racing flat and it's produced by Nike. So how do we know which is which? How do we know which of those two things that make Lunar Racer different from Ghost make them different from each other? Well, that's where we move over to. I have the same trial, but instead of keeping track of the shoe names, I've made this a factorial experiment where factor A, and we can look here, factor A is whether it's a lightweight shoe or a medium weight shoe or a heavy shoe. And factor B is whether it's made by Brooks or whether it's made by Nike. It's the same treatment structure, it's the same number of treatments, but now we have decomposed our treatments into components. So if we print the reports, and this time we're going to need to select factorial AOV. And now what we can look for in our factorial analysis is that we have among the factor A, the light, medium, heavy shoe, we see significant differences overall on the main effect. Lightweight shoes, I tend to be faster. Heavyweight shoes, I tend to be slower. We can also look at the B components, and that is in Brooks shoes, I tended to be slower. I tended to be faster in Nike shoes. Now down here where there's the interaction part, we don't see any significant letters. And this is kind of the interesting, I think, interesting feature of the factorial design is we have taken, let's go back to this trial, where we have these 6 treatments, just straightforward across the board as just treatments. We've decomposed those differences. Oh, took the wrong one. And now we see why there's differences. The Ghost is a heavy Brooks shoe. The Lunar Racer is a light Nike shoe. And the combination of both is what separates those treatments in the RCB analysis. But this can give me information that across the board, the Nike shoes perform better because they have a certain component to them. In this case, the name, let's go, was indicative. The lunar and lunar and lunar all represent a particular type of foam that was used in these shoes. And my thinking is what explains the differences here. So the difference in treatments here, I can further understand by decomposing into treatment components. Yeah. So that's hopefully the brief enough overview. Excuse me, I'm taking another sip of tea, of the general difference between factorial designs and standard randomized complete block analysis. So let's go to the next step then, is what makes a split plot different from a standard factorial design. And I probably should have segued with a different screen here. I didn't realize it was an abrupt transition. When we do split plot, the term split plot means that we take a one experimental unit, typically what we call our whole plot experimental unit, and we divide it up into subplots and then apply the second factor or the second component to the individual plots within that subplot. The common reason for doing this is sometimes, particularly in agricultural trials, there is one component that's easy to add as a bulk across, or it's easy to add It's easy to work with, so you can do it in small plots scattered throughout a field. Others are harder to do, and so you want to do them in one large chunk. This still lets you have a comparison among the different components, but there's going to be a trade-off, and we'll get to that trade-off in a minute, but the randomization occurs at 2 levels. Okay? The whole plot factor is randomized as RCB. It's blocked as if each of the large main effects were a single plot. And then the subfactors are randomized within the whole plots. They're independently randomized within this. Next week, I believe I'll be talking about repeated measures. Repeated measures share a lot in common with split plot, except for this part. All right. And so the analysis of variance, when we look at the analysis of variance, the whole plots as RCB implies that there should be an experimental error at the whole plot level. And that's not going to be the same as our residual error. Residual error is leftover error, but our whole plots are ICB. And so we've got to keep a special error term for that. Well, let's talk about an experiment. So this is one I did. This is not one I did on myself, but this is a type of experiment that illustrates why we would do something as a split plot. And in this case, I decided this little chunk of land, it's actually near the farmstead where I grew up. I'll tell you a little story. At the top of this hill, there used to be a house there. And when I was about 4 or 5 years old, I was outside just playing in the dirt like kids do, and I found a rock that looked like a Christmas tree. And when I came in, well, it turned out that was an Indian arrowhead, which is kind of odd because I don't know if this is a place where you expect a large gathering, that there would be artifacts around, but nonetheless, I found an Indian arrowhead down there. So this land is still in my family, and we still kind of oversee it. Dad set up some trees over here that just kind of took it out of production, and it's been dominated by brome grass. I don't want brome grass there. I wanted to restore it to native prairie. So what I wanted to do is try to figure out how to restore this land to native vegetation. Prairie flowers, cone flowers, lead plant, verbena, whatever. So I decided I was going to do an experiment. And the two things I wanted to test, the 2 components are, what can we do to suppress invasive grasses? How do we get rid of brome grass? Some people, you burn grass. Some people try to mow brome grass to keep it down. And of course, the other is just spray herbicide on and kill it. So these are my one component or one factor. And then I wanted to look at what type of seeds would establish themselves in this prairie versus whether or not the underlying seed bank, the native seeds that were still in there, would reestablish themselves. So I had one where I didn't apply any native seed mix, and 2 others I got from a seed company that represent native flowers and grasses from Minnesota and native flowers and grasses from Iowa. These were slightly different mixes of different seeds. They didn't have a South Dakota mix. So I have this as a 3x3 factorial design. But what should stand out a little bit to this experiment and what makes this a split plot design is if I have 3x3, which is 9 total treatments, in 5 replicates, that implies a 45 plot experiment. If I have 3 different combinations of burn combined with none, burn combined with Minnesota, burn combined with Iowa, I would need to have 15 different burns, 1 for each plot that has a burn as a factor. That's going to be kind of hard to do on this field. And I looked around, I just did not want to have to divide it up into 45 different plots and burn 15 different burns. So that's what drove the choice of making that a split plot design. because then as a whole plot unit, I only needed to burn 5 experimental units. So I had 5 different burns to deal with. Mowing and spraying, it's a little less important. I can manage mowing and spraying on a subplot level, but burning, no, wasn't going to do it that way. So that's what the design looked like, and that's what motivated the choice of being a split plot. And so my arrangement, this is images from mid-season when I was doing some of the scoring. And so this is whole plot number 1, which I believe got sprayed, if I remember correctly. Yep, the sprayed. Whole plot number 2 was, I think, burns, and whole plot number 3 was mowing. Yeah. And you can see that some of these images, there were plants that were established. In this one, the 2 subplots was no seed treatment versus a Minnesota seed treatment versus the Iowa seed treatment. And you can see that these were, I think, partridge peas that were growing up that established themselves well in these whole plot treatments. So that is what it looks like. And let's see. If we analyze this then as an RCB analysis, we have the replicates and the between treatments, the different sublevels, and then our error. This, however, is a bit misleading because we do not account for that nesting. So let's go over and take a look at the actual trial. I think Matt sent you a link to some of these, and I have to move something around so I can get to it on my screen. All right. And I have to move that one around so I can get rid of it. So let's go to prairie seeding trial. Now this has a lot of data. We're not going to analyze all of them. I'm going to go ahead and start the analysis. Oh, somebody, oh, I just saw somebody, I don't know, Magda's joining. So we're going to analyze this as a factorial AOV. And unfortunately, working at home, I have a cat who just decided to come say hi while I'm doing this. Yeah, hopefully it won't make too much noise. We have our factorial AOV table, and we're going to go ahead and let's see, did I not? I have to go make that change. I don't want to do all of them. I want select treatments. Oh yes, check the chat. Matt posted a reminder that if you didn't download the files, he's giving you a link. He keeps track of stuff that I don't, unfortunately. I'm going to go back to my Keynote screen because I want treatments 3, 7, 49, 33, and 36. Those are the ones I chose for this one. 3, 7, and I'm putting 49, 33, and 36. Now, you should have gotten a file that had images removed. So yours probably won't have those little red bars if you're following along. So let's take a look at what this is telling us, shall we? We have in our decomposition, well, the first thing we want to do is look at the error terms. So we have in this analysis an extra error term. Let's go back to my Keynote slide. I think I have that written there. And so we see that we have our between A is, again, the decomposition of the treatments A, B, and AB, but there is additional level of error And actually what we're doing is decomposing some of the residual sums of squares. So, there's error 14 and error 9. So with the standard factorial design, we decompose the between treatment sums of squares into A, B, and AB components. With the split plot, we also decompose the residual error sums of squares into an error for A and an error for B. Now, the reason I picked one of these data columns, it kind of illustrates this. So let's start with that one first. In this one, column A, notice that I have no error on the B level. Okay? Column A is when I took pictures, and let's see if we can do it this way. When I did this, when I set up the trial, I took pictures of the whole plot. So I had 15 pictures that were each, let's see, move things over, go over assessment data. So if I clicked on plot number 101, I don't have images associated with 102 and 103, because that's the image that's associated with that whole plot. And that's what the whole plot looked like after looks like a burn. That wasn't a very good burn. In fact, it don't look much different from that one. Did I get that mixes? There we go. Let's see if I can find a good looking one. Oh, there's one. So that's what the burn looked like for that whole plot. And so what I did is I converted those images to red, green, and blue color scale just to have a continuous variable to have in there. But since I only had one value for each of the subplots, I had to enter the same value for each. That means when I do the analysis, I do get a decomposition on the whole plot factor A sums of squares, but I don't have any decompositions of the B level factors. Where they do any decomposition is effectively zero, because the means are going to be zero within the whole plots. But it works out in the analysis because I do have the error term for the whole plots. And that error term is capturing all of the experimental error at that level. So since I only had one picture for each of the whole plots, I am able to analyze the whole plot as RCV. This is what I want to emphasize with split plot, is whatever you do at the whole plot level will be analyzed as if it were RCB at the whole plot level, which means in this experiment, even though I had 45 subplots, I can only compare my whole plot, my burn, mow, and spray, as if it were an RCB of 15 plots. And that doesn't, it's the same as if you had done an RCB with subsamples. The subsamples don't give you any more information about your experimental error. And in this case, my experimental error with regard to burn, mow, and spray, let's see if I can find that one I just popped up a little bit ago. If we take a look at that one, oh, did that disappear? And we take a look at that one. Where did my window go? That looks like a more effectively burned plot than the first one I showed you. That's the experimental error that's applied across all three subplot treatments. Okay. So when we do the whole plot error, we are looking at the experimental application of something as a single unit. So this is why we need that two-level decomposition in the split plot. Now, the next one, let's see if I can remember what interesting thing about it was, is whether or not the color, this is the color green for about 2 weeks later. And we see from this decomposition that there are differences among the whole plot levels. There's also some difference in the B levels, which is really kind of surprising. Well, there are some differences in the, well, not really significant, I guess. So there's minor differences in the B levels, not enough to be significant. And so we don't see any differences among the seeding means at this level. We do see differences in the main effects. The differences at this level, at this point, there shouldn't be any treatment differences there, but it does indicate to me the patchiness of some of my application of that split plot treatment. Specifically, the herbicide sprays I did were not as, I didn't apply the herbicide as well, so there are some parts of the whole plots that were less effectively treated than other parts of the whole plot. Again, backing up, this is a compromise with the split plot design. It was more effective for me to burn a large unit. It was less effective for me to spray a large unit and do it uniformly and consistently throughout the whole unit. Well, this is a trade-off that you need to take into consideration when you make choices about split plot versus standard factorial designs. Is when you do the large whole plot, you have to be able to do it uniformly through a larger area than you would do in a small plot. Okay? Because that is going to affect your error term differently. And then finally, the other 3 columns are, again, the September color, which is this map here. And you can see by some of the vegetative growth that we do expect to see some differences in colors. And it also corresponds to differences in the types of weeds that I counted. So let me back up. Oh, I don't think I wanted, well, yeah, okay. So the 2 assessments I did, I thought I had a different column selected, but this one will work. The 2 assessments I did on September is I took a picture of the plots, and I also counted the number of invasive non-native species, and this is what pigweed, which is just a nuisance weed that pops up. And then I also looked at coneflower, which should only be in the treated, the treated seeding, the Minnesota seeding and the Iowa seeding should not be found in where there's no seeding, whereas the pigweed should be evenly distributed across all of the subplots. And it's nice that I get this overall treatment effect, or excuse me, that I get this no difference at the seeding level of these weeds. And I can't say that there was a difference in preparation, although it is suggestive that the spraying did a better, didn't really control pigweed when I sprayed it, but the burning and the mowing knocked out the pigweed. So that's a little, that's information that I can get from a split plot design. And if I look down here, I can see that the burn and the mow and the burn and the mow and the burn and the mow were consistent with not having any real counts of pigweed. And it is the spraying and the spraying and the spraying that had the main effect. Now, let me see if I did this right. Yeah. So if we go back to the ANOVA table for pigweed, we see that the whole plot level, not quite enough to be significant. Although there is suggestive that there may have been a difference in the preparation methods, and there should have been no apparent difference in the seeding because we just don't expect seeding to have an impact on that. We do see in the coneflower count that there is a difference in the mowing, there is a difference in the seeding rate, and there is an interaction between the two. And so the Minnesota, let's try to make some sense of this. First off, it was only the sprayed parts where the coneflower established itself. Burning and mowing seemed to have no effect on establishing this introduced species. Okay. There seems to be a difference between, well, maybe a difference between the Iowa mix and the Minnesota mix. The letters they're overlapping, even though the numbers are quite a bit different. And partly because these numbers are overlapping because of that interaction. Because we have this is being measured across the different establishment stands, we kind of average out those effects. And we only see in the interaction part where the sprayed and Iowa treated plots showed a small number of coneflower seeds, where the sprayed in Minnesota plots had about 3 times as many coneflower plants. So this kind of illustrates the difference between what we would interpret from the main effects, that spraying has an effect on coneflower, but the other two didn't. And we are questionable whether there's a difference in the seeding mix. But when we take into consideration the interaction of these other two non-effective methods, that we can make some statements and compare Minnesota and Iowa under similar conditions. So that's going to lead me to the last bit that I want to cover. And something we need to keep in mind when we're doing this. So we should have covered these already. Is we need to have a brief review of standard errors. Normally when we do a standard error, and I'm using LSD for convenience, when we calculate a standard error, or calculate a mean comparison, and I'm using LSD because it's simple, we take a standard error, which is our, in the simplest case, our residual standard error times 2 divided by our number of replicates. If we have unbalanced observations, we use a slightly more complicated formula. And this might come back to us in a minute. But we take our measurement of error, and then we add a fudge factor for the sampling distribution in order to get something that's convertible to a p-value. And so our LSD is at a certain 0.95% two-tailed, gives us our measure of difference that we are going to say whether or not these things are significantly different. This is standard for RCB designs. Okay, so one error term is sufficient for all the comparisons. Now, when we get to factorial, we have to take in consideration, if we were going to make comparisons at the whole factor level, so factor A, main effect level, we are going to have more observations of that because that treatment was done in combination with several other things and divided up among several other things. And there are B numbers of those other things. So we divide our residual error by a larger value. Similarly with the B effects, we divide our residual error accounting for the number of A factors. And then when we get to the interaction level, we only have the single replicate term. And so the main effects have more observations. And so we can have a smaller error when we make the main effect comparisons. So if we look at, I think this is the first one I showed you. If we do an LSD, the RCB analysis, we only have one LSD value. But if we compare main effects, we see that we get a pretty meaningful increase in our LSDs when we compare, it was shoe model versus or the shoe weight. So this is an additional advantage we get from factorial designs if we care about measuring those components. Now, split plot gets more complicated because, as I've tried to emphasize, when we do a split plot experiment, we have the whole plot error. And so this is the mean square error A. And then we divide that by the additional number of observations we have for the subplots. When we look at the B effects, we can also divide by the number of A levels, but we can use the residual error. And in this case, I've denoted as the mean square error for B. When we look at the interaction, we have only a small error term. So let's go back to that. Oh, I didn't close that report. So when we make this comparison here, okay, we are using a different number of replicates and a different error term. And so we have a different HSD printed on this screen that we need to get over that hurdle. Remember, these means are averaged out over all of the combinations of preparation. When we get to the interaction and we look at the individual spray in Minnesota seeding versus spray in Iowa seeding, we haven't averaged those out over the different levels. We don't have as many observations, but we also have a change in the center of the mean. So we need a larger HSD to get the significant difference. But we also have dissected out what is our potential interactions. Okay. So if you would look at, in your reports, you will see that there's going to be individual error terms listed. And we also show these error terms in the ANOVA table. And again, to emphasize, whole plot error gives you a different calculation than subplot error. Now, there is something going on in the background that we don't really show. Is subplot components combined with different whole plot levels do not have the same error. And we'll take a moment to explain this. Let's go back to this. So if I want to make a comparison for some reason between the Iowa seeding on sprayed plots versus the Minnesota seeding on burned plots, I have never had those two combinations together. I only have Minnesota and Iowa compared together in a burn plot, or Minnesota and Iowa compared together in a sprayed plot, or Minnesota and Iowa compared together in a mowed plot. But I never have Minnesota and Iowa together in that odd combination of spray and burned. Now, in a factorial design, I would have those combinations appearing together in the same replicate. But because we never have those combinations appear together in a single experimental unit, oh, where we go, we have to do some fudging to account for not only that residual error, but the whole plot error. And so there is an additional LSD on this screen and HSD in the report. We don't show them in the report. They are calculated internally when we do the mean comparisons. Okay. It's not as important, I think, to report that, because usually you don't really care about the crossways comparisons. If you do care about those kinds of comparisons, if those are really important, you might need to rethink how you structure your split plot design. And that should be the final takeaway for this discussion, is the factorial designs allow for more precise comparisons among treatment components, because you can divide up your treatments into the effective ingredients and look at those individually if you have them balanced. Split plot designs are useful when one treatment component is more difficult to apply than the other components. But you have to be careful in your choice of your whole plot components, is that they will be compared with less precision. And I made it in my experiment. I made a choice, and it was a necessary choice because of the way of doing it. I was more concerned about the difference between burning and mowing and spraying than I was about the difference in the seeding. But the mechanics of doing the burning and mowing spraying forced me to accept a larger experimental error on those effects. And I think that pretty much covers the key ideas that I wanted to talk about today. I guess if we can type some questions in, or maybe Matt, if you want to open up and answer questions, I'll see if I can't log onto a different machine so I can hear. We do have a little bit of time left. Well, I don't have any date to go. I've got no dates tonight, so I can stay here for a bit. All right. I'm going to leave this up. Let me see if I can't log in on my other computer and take some questions. Woo, look at all those questions. Good. So the first question, Eric Ellison, how many whole plot replicates suffice generally? It's going to be the same answer as if you were only doing the RCB with that treatment. So here, 15 whole plots was what I could fit into that field. And so I accepted that I was only going to have 15 whole plots. If I were doing this, getting paid money to do it, or it was more of this is an idea that I wanted to test. So if I were going to do this again, I would probably try to have, let's see, how many degrees of freedom? We want a minimum of 12 degrees of freedom from our experimental error. So 3 treatments, 6 replicas was give 18, probably looking at 8. I'm guessing 8 off the top of my head would be better. And yes, it's because when we have the whole plot level as RCB, we lose degrees of freedom. Carmel Ryan asked, when comparing at the whole level as RCB, there would be low degrees of freedom. But that is what we have when we consider the experimental units and what experimental error means. I think about experimental error is what can happen in the application of a treatment to an experimental unit. And so if I applied a treatment to 4 plots simultaneously, those 4 plots are not independent experimental units. Okay? They're now the same experimental unit, they're just divided up. It's divided up into smaller pieces. So when I do a split plot trial, I will accept that my whole plot is going to reduce my degrees of freedom for error. And so that's a choice that you kind of need to balance. Is you do gain degrees of freedom for your subplot level. You do gain degrees of freedom for your interaction, but your whole plots are still just one experimental unit. And Sandra Alcatraz asks, when you run the same trial in multiple locations, do you consider the whole plot component? Yes, you should. I don't know if we have ARMST set up to do that properly, because the error term gets a little more complicated, getting the error terms to balance out right. Because when you do multiple trials, you can fudge a multiple trial analysis if you have RCB as doing the trials as the whole plot, and then the replicates within trials as a subplot. You don't decompose your error terms quite the same way. Okay? And so we tend not to do we haven't yet worked out the background calculations to properly do combined split plot trials. To really do it correctly and to be clean with it, we need to work mixed model analysis in. It is a similar concept when you do multiple trials as you do split plot, as you have a hierarchical error term. And you do basically look at your different levels of error. And it's a similar thing with any other question is, how precisely do you want to compare your experimental treatment, and how much variability do you think you need with each trial? So again, it's still thinking of that whole plot treatment as, if I were going to do that as an RCB, do I have enough observations to be convincing on that main effect? So I hope I got those questions answered. I had 3 pop up that are pretty similar. And they're all, it is, and I think this is what I want to emphasize with split plots, is you are gaining some degrees of freedom for error for some of your combinations. I guess the other thing I wanted to, that we run into occasionally, is what's not a factorial design and what could be. So I also did a trial. Again, I did a running shoe trial, and I chose, I kind of chose my models that had different foot technologies, midsole technologies. So I have a midsole fulcrum from this one company, Carhu. And then I did find this has a 4-foot, which is these weird levers on the front of your foot. And then I had 3 standard shoes. Well, it turns out that when I run the report on this, I didn't in this experiment. Oh. I don't know what I want to do. Did not see any significant differences here. And unfortunately, because I did not structure my treatments, I wanted to know, I wanted to know if this particular shoe company, this Carhu, that had this thing in the midsole, this lever in the middle of the shoe, well, that was an effective technology. But the way I set up the experiment is I really can't necessarily test the technology as opposed to testing the shoe manufacturer. So the way I set up this treatment structure is I put these comments in here that tell me something about the models themselves, but I did not break this down into treatment number 1 has fast 1 Carhu midsole, 2 would be fast Carhu midsole. And so I didn't really discover how I could have reorganized this into something that would say, give me 2 standard shoes and 2 midsole shoes, or 3 standard shoes and 3 midsole shoes, and give me a treatment structure that I could hope to dissect out the specific shoe differences from the general shoe technology. So one thing to consider as you go through trials and you start filling out these forms and have a lot of components, we're kind of working on and hoping to be in dialogues on how we can restructure this to help you discover factorial designs from RCB experiments. So if I run into you some later on, that's going to be a question I might be bugging you on. All right, have I covered everything? I think we've used up our hour. So if there are no other questions, I thank you all for coming. And I will be back online and hopefully have my sound issues worked for tomorrow morning. So if you have any questions, you're free to come in and chat. Otherwise, have a good day.